Welcome back, students. Please settle down. Please settle in, everyone. We're just a few minutes away from restarting the session. So please settle in.
Shielding Earth from numerous radioactive things and all. And today, let us see what new facts are our Sir Girish sir going to share with us. Yesterday, we came to know about various Chandrayaan and many other programs of ISRO, which can really be a great achievement not for India but for the entire mankind. So really, we are really proud that we have one of the most important department which made our India proud, that is Department of Atomic Energy and ISRO leading the science program. So we are really blessed to have these great personalities here. They are sharing the ideology, the vision on which they are working. So this really is a journey of patience, how India from being a developing nation is gradually moving toward being a developed nation. So our wishes are with them, and let's hope so that you too can grow up, and under their guidance and mentorship you can also join these departments, these, you can say, the think tanks of our country, and you can also contribute to our nation development. So with this, I think our Sir Girish sir is ready again to fascinate you with some other ground, you can say some other fascinating presentations which will lead you to more awakening of technology, having more ideas which could really be a, you can say, life changing event in your life.
Acho. Thank you. Thank you very much, and sorry for the delay. So, how many of you seen this note, 2 rupee note? Oh, fantastic! Not bad. I thought that the 2 rupee note gone bad long back, gone out long back. So, our ISRO's entire story is based on from 2 rupee note to 2000 rupee note. Unfortunately, both of them are not in circulation now. So, our journey started with what is that satellite? Aryabhatta, and then Mars mission, Mars orbiter mission, not our mom. So the journey, you can clearly see that ISRO has galloped 1,000 times from its humble beginnings using sounding rockets. Sounding rockets are nothing but the rockets which makes when it goes up, it stays in the space for say some 10 minutes or maximum 15 minutes, and then it can actually help us study up to from up to 200 kilometers. So we started from there. Now we have reached moon, Mars, and we are planning to go beyond that. Okay, this my entire talk or India space science program is those two. No? So my talk is astronomy from space and beyond. Any idea what are these dots? Satellites. Very good. So if you see these satellites, since I don't have pointer, I'll be moving closer to this one often. And before I begin my talk, I just want to steal the quote from Sir. What's the Sir? He said that Department of Atomic Energy uses all parts of science from physics, chemistry, and I can say that we also do the same thing. And we go beyond that. We go even to biology and other things, including political science, because we need money from government. So if you see this image, you can see that there are multiple orbits here. Okay, I'll be talking about these orbits later, but just to give an idea about this figure, you can clearly see that there is a concentration of satellites close to Earth and another orbit here. So these two orbits are mainly used for most of our space program. Okay, so one of them very close to one is called as low Earth orbit, which is around 500 to 650, 700 kilometers. And then another one is called as geosynchronous orbit. So since the name geosynchronous, that is, it is synchronized to Earth's rotation. That means that since like yesterday, whatever we heard about moon and Earth, the way only one face of moon is always visible from Earth, we are putting the other direction now. So from geosynchronous orbit, one face of the Earth is always seen. This is useful for communication because we want that to look like a stationary object as per the Earth, the person and the Earth, because both of them will be moving in the same direction. That's what geosynchronous orbit is. So why do we do space exploration? So most of our space exploration is trying to answer three fundamental questions. First one, how exactly all these come into picture? How did the universe came into existence? Do we understand how galaxies, stars, and everything came from and from where it came from? That's the first question we try to answer, and Sir will be talking about that later. And then, what are the laws which govern this universe? So are they very randomly done, or are there any specified rules and conditions which this universe follows everywhere? We heard one most important rule yesterday, that is speed of light. Okay, speed of light is constant and it is around 3.3 lakh kilometers per second, is a well established rule that entire universe follows as of today. So like that, there are many other conditions. Kepler's laws, you know that everything follows Kepler's laws, and this Kepler's laws not only applicable on Earth, throughout. So entire universe can be explained with this fixed number of rules. Then the next question, or the final question, is what's going to happen to this universe? May not be today, may not be tomorrow, may not be day after tomorrow, but after few million billion years away, what is going to happen? So that's a third question we are trying to answer. So the study of space mainly is the study of stars and galaxies and other famed objects. For these studies, we use multi-messenger. Multi-messenger means multiple tools or multiple radiation to study these things. Mainly three. The first one is the well-known thing for every one of us, electromagnetic radiation, starting from radio to gamma rays and beyond. The second one is a latest one, new one, that is gravitational waves. Even though we were trying to find gravitational waves from very long time, we succeeded few years back. So that's what that he asked a question about gravity. This one particular black hole with light around that Event Horizon Telescope. That is the image from the Event Horizon Telescope. But now we actually measured gravitational waves as predicted by none other than who predicted gravitational waves? See, if you don't know the answer for any of the questions related to physics or maths, you say Einstein. Okay, so 50% of the times the answer will be correct, better than zero. So then there is particles. So all around us there are particles coming from cosmos, and I don't know how many of you believe me if I say that there are thousands and thousands of particles just crossing through, means passing through us as I'm speaking. Almost 50,000 particles per second are passing through us. Can you believe me? Not only me, with you, in you. These are called as neutrinos. So neutrinos are generated. These neutrinos are mainly from sun because they are very close to us. And these neutrinos are generated at the core of sun in the fusion reaction. So these neutrinos are massless, chargeless, so they react very less, and hence they simply pass through us without even we knowing that something like that is happening. So these are the these are the three things which you use to study the cosmos, but for all practical purpose we mainly use only electromagnetic radiation. These are like error bar in that 100% electromagnetic radiation plus or minus 0.01 or zero 0.1, whatever we call, is 2. So for millennia, from the day the human came out of the caves in the night, started astronomy. So as he saw the sky, he started wondering, where are all these twinkling light coming from? And where do they vanish during the daytime? So will they go on? So this is a question which actually started astronomy, as you are well known. For a long time, very long time, using your naked eye as the only way to actually understand cosmos. So that's how cosmos looked long back, and even today it looks like that. And now it has moved to more sophisticated tools and telescopes, sensors, and all sort of things. Why? Okay, I'll ask you a question. Have you any time thought of how many stars you can see in the sky with your naked eye? Best sky, not in a city like Bhubaneswar or Bangalore. Very faint, like fairly dark sky. How many stars can you see? Don't say infinite. How many? Just some number. Few millions. 200. Okay. Any other number? You should actually try to guess. I told you 10. Give some numbers. Hmm? Ah. How many stars per square degree? How many? No, because the problem is most of them may not actually see the sky in the dark place. So at any time, we will see from a dark place around 2,500 to 2,600 stars only. And throughout the day, if you see, it will be around 5,000 to 6,000 stars visible from any place. It's not millions, it's not 200, it's around a few thousand, 5,000 approximately. Okay. These are the stars we see. The faintest star, we call it as sixth magnitude star. Sir will be talking about those things later. I'm not going to touch into that. And because that limit comes in the naked eye because of limit of our eye. What is that? Two limits actually. One is the size of the pupil. What is the size of the pupil? Maximum 10 mm. Okay, on an average 6 mm, but maximum 10 mm. What is the second constraint? Second constraint is our, okay, I'll put it in answer. The answer for that is the movies. What am I talking about? Have you any time seen how the movies are made? Not the latest digital, huh? Persistent vision. What is that persistent vision? 120, usually 1/20th of a second. Any photo which forms on our retina will not stay beyond 1/20 seconds. So why this is a constraint? Because if it is a fainter source, we cannot keep on integrating it. It will simply vanish. So we can't actually keep on adding. So these are the two things which actually limit our eye observations. Yesterday I talked about moon in the night. It looked like bright moon because they could actually integrate it for very long time, which we cannot do here. So madam will be showing that with a integration of some 10 to 20 seconds, the night will look like day. Okay, because you can keep your camera shutter open for so long. So that clearly shows that our eye limit comes from these two factors. So what is electromagnetic spectrum? Sir actually mentioned about this, starting from radio, microwave, infrared, UV, X-ray and gamma. This is the only portion where our eyes are sensitive to. So below this infrared, whatever sir talked about 1 degree increase in the temperature, we cannot see anything. Beyond this visible, UV and others are not seen. So our observations are limited to only this area. Okay, that is very narrow range, 380 to 700 nanometers. Most of the times it will be within 650 nanometers. Okay, so Earth's atmosphere blocks most wavelengths. So the reason for these things is because UV rays won't reach Earth in most of the places. So our nature did not actually modify our sensors or eye to make observable. That one is observed from Earth. Okay, so before going to actual observations, I'll talk about the last centuries famous detections or discoveries in astronomy, starting from Milky Way. So now we know that Milky Way is not the only galaxy. Okay, other than Milky Way, the only galaxy which was visible to naked eye is Andromeda galaxy. Sir mentioned about that yesterday. So then we know that universe is expanding. It's not static. It is expanding. Now we also know that how exactly the energy inside a star, in particular a sun, is generated. So people will actually ask, sun is burning bright, but where it's getting oxygen? This is a common question asked by many people. It is not using oxygen to burn. When we say burn, it's actually we are talking about nuclear fusion. Two small nuclei combining together to form a slightly larger nuclei. In this process, it loses out some matter which gets converted into energy. Who said this? Einstein, yes. The most famous physical equation known to humans in on Earth as of now is equal to mc square, the most famous. Then we now know that it's not all the stars do not look like the same. They vary, they have different varieties, and we know that some of them are main sequence stars, some of them are dwarfs, means almost 10 times smaller than our Earth, few thousand kilometers, and some of them are much smaller than that, like city of Bhubaneswar, few 100 kilometers in size, and some of them do not have any physical entity at all, like black holes. So we know that they are called as dwarf, white dwarf. Some of them are called very small, very dense, almost like a nuclei. It's a nuclear neutron star, and black holes. These are the end stages. We know the most of the times the stars spend their life in the main sequence, very boring age, like a middle age of a person. When the person is young, he will have a very exciting time. The close to the end also will have exciting time. In between what going through is the middle age, that is the main sequence. Main sequence is nothing but at the core of a star, the hydrogen is combining to form helium. This we call it as hydrogen burning stage, and this is the stage what we call it as main sequence, where more than 90% of its life of a star is spent. So we know that what is the composition of ordinary matter throughout the universe, not only on Earth. And then we know why there are exotic objects like black holes, neutrons, stars, and gamma ray bursts. Gamma ray burst is a very exotic thing, because I'll just give you some idea about that. Sun mentioned that sun is around 5 billion year old. Okay, just take it from me that sun is emitting 33 zeros followed by 1. So much of arcs of energy per second. 10 to the power of 33 arcs per second, sun is emitting energy, means he's giving out energy. And he has lived for 5 billion years, and it is assumed that he will live for next 5 billion years. So this 10 billion years, sun is giving so much of energy. So we are all feeling very hot, and he's the one who is responsible for each and every motion of Earth. Imagine you combine this entire energy over 10 billion years and give it out in a fraction of a second. How much should be the energy? That is the energy carried by gamma ray bursts. These are the most energetic events in astronomy in our universe after Big Bang. Okay, and on an average, there is one gamma ray burst happening in the universe everywhere, but it is random in direction. We cannot actually today which direction next gamma ray burst is going to happen. So then we know that cosmic ray background. Somebody asked yesterday one question: how are we sure that Big Bang happened? One of the proof for that is the uniform cosmic microwave background. I'm not going to tell any of these things in detail. Then we know that not everything in the universe is visible to us. So there are something which is not giving out any electromagnetic radiation at all. Since there is no electromagnetic radiation, we cannot see that. Okay, that we call it as dark matter. And now we have almost not only our solar system, there are hundreds and thousands of solar systems outside. As of today, we have more than 6,500 exoplanets, planets beyond our solar system discovered. And then we also know that there are neutrinos, what I talked about, the particles which are going through us as we speak. Solar neutrinos we have discovered, we have identified, we found how much neutrinos are passing through Earth. And then helioseismology. Helioseismology is my favorite subject, because when you go to a doctor, what's the first thing he does? What is one signature of any doctor? Stethoscope. Fantastic. What does stethoscope does? Amplify the sound. But I am also speaking something. You are hearing me. Then without stethoscope, can you say something about me? Why do you need a stethoscope? Why do you need a stethoscope? To hear the faint murmurs. Okay. So what exactly a doctor will do with a stethoscope? As soon as I go to a doctor, my doctor will keep the stethoscope on my back and say, cough. Have you seen this? Why he's asking that? What exactly he's checking? Why he wants me to make some sound? Underlying sounds can be, but he's asking me to cough. Without that, he could hear that. Okay, so coming to our sun, whatever the information, whatever we are getting is coming from only the outer photosphere, few hundred kilometers depth. Okay, but know that nuclear fusion is happening at the core, 6 lakh kilometers deep. When in a nuclear fusion, how many of you have studied nuclear fusion? Hydrogen plus hydrogen is equal to helium. How many of you heard of hydrogen bomb? Hydrogen bomb. Fantastic. Hydrogen bomb is nothing but nuclear fusion. So what is the kind of energy given out in a hydrogen bomb? In which wavelength? They are very, very high energetic radiation, gamma rays. But what we see from sun is it gamma rays? What are we seeing? Optical light. So what is happening in between? So these gamma rays, the center of the core or the inside of the sun is so dense that it is not allowed to walk or move, cross more than 2 centimeters before it actually collides with another particle. So then another scatter. By the time it comes out, there will be millions and millions of scattering. So it would have lost all its energy. From gamma ray, it would have turned into photon, means optical photon. So it would have lost all the information about what exactly happened inside. So that says that even if you send Superman inside the sun, see more than 2 centimeters because his X-rays will be reflected before 2 centimeters. Okay. Now, hence, whatever the information we are getting from the outer portion, if you want to actually get the information about what is happening inside, how can you do that? That's where helioseismology comes. Seismology, you heard, right? Earthquake is nothing but seismology. You are measuring sound. So go back to doctor. So the doctor will keep this one and he listen to the sound what is you producing inside the body, mainly say in your lungs and others. Depending on your visual, like visual you can use, visual length, depending on the length, the pitch changes. You know that harmonium works like what is the length from where it is reflected. So similarly, don't take this as a actual answer, but assume that our lung is filled with water. So depending on how much it is filled, the pitch changes, right? Just by listening to the sound, he can actually say what is happening inside the lung. Similar way, we know what is happening inside the sun by studying the radiation or the way it is vibrating. The sun is vibrating. How it is vibrating and measuring the frequency with which it's vibrating and everything, we can actually study what is happening inside the sun, which is not available with photons. Okay. So even though it is not a multi-messenger, because anyway for this also we use electromagnetic radiation, we use seismology to study inside the sun. If it is sun, it's helioseismology. If it is stars, it is astroseismology. With this, we can actually use it as a probe to study deeper inside. Sir will be talking about this also tomorrow. Today. Okay. Coming back to what are the celestial objects we study using these telescopes and the multi-messenger is usually planets, moons, asteroids, and comets within our solar system. If we go a little further from solar system, we have main sequence stars, white dwarfs, neutron stars, rotating neutron stars called pulsars, and black holes. Then group of these stars called binary stars, X-ray binaries, globular clusters, and even star forming regions in the galaxies where the stars are getting formed even now, nurseries. And then finally we can go to the higher and higher size galaxies, active galactic nuclei, quasars, galaxy clusters. Sir talked about moons, which is around 3,000 kilometers size to parsec. Parsec size is kiloparsec size. 1 parsec is 3 light years. kiloparsecs is 3000 light years, the size of these things will be in the parsec range. Okay, so many orders of magnitude we study, and the smallest of these objects is neutron star, which is around less than 100 kilometer in size, and black holes. So from where actually we do all the studies, we have mainly multiple vantage points. So already talked about low Earth orbit, which is very close to the sun, Earth, and then geosynchronous orbit. In addition to that, if we can see, there are few orbits which are going like this. Okay, can you see them? So these have different names for that, but some of them are very, very long. Okay, so when I talked about geosynchronous orbit, if you are here, Earth, sorry, our India is somewhere here. So if you place a satellite here, it will be actually following this all the time. What if, like Russia, you are very close to the pole? So then you will not have, you cannot have a orbit here, na? That's where these very, very long orbits comes into picture. We call it as Molniya orbits. Okay, Molniya orbits are used to give long coverage over poles. Not only that, sometimes these orbits are also very, very long, because if you are making observations from behind on around Earth, whenever it goes behind Earth, then there will be a gap. Okay, Earth itself will act as a block, occultation. So to avoid that, some of these missions uses a very long orbits where the occultation is very, very minimal. You go farther away, continuous observations, and then come back. Okay, so in addition to that, there are 5 points between sun and earth called Lagrangian points, where effective gravitational field is 0. Effective. Okay, just to give an example, sun has a higher mass, higher gravitational field. Earth has lower mass, so lower gravitational field cancel out. So you are using it as a two gravitational forces for pulling something apart. So at this point, the gravitational field will be 0. So those are called as Lagrangian points. Okay, so there are totally 5 Lagrangian points: L1, L2, L3, L4, L3, and L4, L5. Okay, and have you heard of Trojan? Trojan horse story, which is that movie, Brad Pitt movie, Troy, Helen of Troy. So he used a wooden horse to actually infiltrate. What is that? Sparta, which is that place? Okay. So those Trojan, but the Trojan did not come from mythology. It came from the asteroids which get stuck in the L4 point. These are called as Trojan asteroids. We have used in L1, for example, which is the first solar observatory from from India? First solar observatory. Please. Aditya. What's the full name of Aditya? Aditya L1. That L1 comes from here, Lagrangian 1. So the reason for going here is it will give us continuous coverage, because this L1 will be moving along with Earth. So at 24 hours, you can actually, without blinking your eye, you can continuously see sun, which is very essential for some of the observations. So the sun, Earth is, the Aditya L1 is kept, and most of the solar observatories are kept here. Not exactly this point, because if you keep it here, what happens? How many of you watch TV? DTH. I really want to ask you, haven't you TV at all? You are the only one. You too, both of you. Because you are the ones who did not raise your hand. I'm sure that either you're lying or you are sleeping. Okay. Whenever you watch the TV around 12 o'clock, what happens? Suddenly you see some disturbance, right? Haven't you observed it at all? When your satellite is just in front of the sun, you will see some disturbance. So then you will see that the disturbance may be because of solar interference. Means sun is so powerful emitter in almost all the wavelengths that the radio waves coming from sun will actually more than whatever the satellite is emitting. Okay, so the same using the same analogy, so sun is emitting so much light that if it is in the field of view, you will not get any signal at all. To avoid this, what we do is we'll not stay here, we'll go around this point and orbit around this point. This orbit is also not small. It's 1.5 million kilometers. As if it is the distance between L1 and that itself is that the size. Okay. Even though I say Aditya L1, it is not staying at L1, it is going around L1. Okay. And we have usage for L1 and L2. We are sending another mission called ExoVerse. It's going to study exoplanets. We are going to put that in L2 because it's going to observe in infrared radiation. And we even have use for L4 and L5, but we haven't got any use for L3 as of today. So question is, why do we go to space? You have heard of Hubble, right? Hubble Space Telescope, HST. HST took almost 25 years to build. Very, very time consuming. And HST carries 2.4 meter size telescope. In the evening, you will be actually seeing using 8-inch telescope, whatever we have here. But we are talking about 2.4 meter size. 2.4 meter is almost like this large. When it was launched, it was as big as double-decker bus. Okay, and the cost of that is almost 100 times more than similar telescope, whatever we have put it in Hanley. So it's very, very costly. And if something happens, repairing will also be very, very costly, which happened with Hubble. Initially, when Hubble was launched, all the images were blurry. So they have to literally use a spectacle to correct that. They calculated what is the eyesight of Hubble and put a mirror in a lens in front of it. You please read about it. And how did they do it? They launched a mission to carry this repair crew, go there, replace, and put more fuel and come back. So that's the kind of thing which actually requires, and because of that, it has completed 25 years in space and it is going very, very strong. Okay. It's very, very costly. It is very, very time consuming because both of them is because the temperature when it is towards sun, it can go up to 100 plus 100 to plus 150 degrees centigrade. When it is away from that, it can be as less as minus 150 degrees centigrade. Not once, every 90 to 100 minutes, it will be happening. It goes through cycles. So it has to survive. It has survived for 25 years. So that means that whatever the amount we have to spend is so high. Okay. So then comes radiation. Sir talked about radiation. Particles will, lots of particles are outside, which are actually, which can actually cause lot of destruction. But luckily, Earth has magnetic field around that, which will be moving it away towards poles. So where do you have seen this? Aurora. Have you heard of Aurora? Aurora borealis is happening because of these charged particles when they enter the atmosphere near the pole. These charged, we are actually saved, not only electromagnetic radiation, we are saved from charged particles also because of this. But if you go out of that orbit, so then these charged particles will also actually avoid. Whatever Sir was talking about, that effect of radiation on humans, the same thing much at more higher effect. So we have to survive that also. So with all these things, why do we need to go to space? Two things. One is, as Sir mentioned in the first talk, UV rays won't reach Earth. If it had reached Earth, all of us would have got cancer. So it's a boon that it is stopped by ozone layer. But if an astronomer wants to study in UV, then he has to go out because our atmosphere is blocking. Not only UV, X-rays, gamma rays, infrared, and everything is stopped by the atmosphere. Then no seeing. I'll come to this later. I'll come to this saying later. Then continuous viewing, as I mentioned, at some portions you can get continuous observations. So this is a picture of electromagnetic radiation and how much of that will be reaching Earth. If you see that there is a very small window which actually reaches Earth. For all of them are stopped at certain height, 10 kilometers to 40 kilometers and more. And radio also reaches Earth. Okay. So if you want to study anything in this range, from gamma to this one or in infrared, we have no other choice than to go to space, even though it is time consuming and everything. But why do I want to study in infrared or UV? Why can't actually I do all the experiments and everything, observations in visible itself? Why I have to spend so much time? This picture you remember? Okay, this is the same thing, wavelength. This picture showed picture of agent's wife. I'm showing the picture of his guard. Okay, this is the first X-ray image of a guard. You can even clearly see the keys he is carrying. Okay, so if you use visible light, you can see what is happening outside. You can see my face. But if something has happened to my bone, the only way to check that is cut open and see whether there is a break. So that might actually will be more disastrous than the broken bone itself, right? But X-rays opened a new window for that. Now, without actually like cutting open any person, you can see if there is any breakage. So with just one more wavelength, we got more information about the person than what the light, visible light would have given. So continuing in the same analogy, I'm sorry. That will be very less. So background is more important. So why wavelength, multi-wavelength? You know this images, this story? This is one of my favorite stories. Not only in India, it is there in almost all cultures, including Japan and everywhere. So 5 blind men were asked by the king to actually say how the elephant looks. So each of them touched one portion of the elephant. One guy touched its ears and said that it's almost like a big fan. Another person touched its tail and it said that it is like a rope. Third one said trunk and he said that it is like a snake. And the pillar and then a wall. Who is correct? Who is wrong? Who is wrong? All of them are wrong? Who is correct then? None of them are wrong. All of them are correct. But whatever the little information provided to them, from that, whatever they could actually get an idea is what elephant looks like. Unless and until you combine them together, will you get the full picture? So to get the full picture, you have to put all of them together and then give a uniform thing, something like that. Then you can get an idea how the elephant is. So what it has to do with our astronomy? What is this? Our sun. What are those dark spots? They are not dust. These are called as sunspots. Sunspots are the places where the temperature of the star is and the sun is slightly lesser than the surrounding place. So at all the bright thing, it is around 5000 to 5600 Kelvin. In the sunspots, it will not be very, very less. It will not be completely zero. It is only some few hundred degrees less, maybe some 200 to 300 degrees less. So hence it looks darker. I'll give you the answer why it is look darker. Because if you actually study black body radiation, then the intensity of radiation goes as T to the power of 4. So 200 to the power of 4 is a massive number, hence it looks dark. Okay, that means. Then this clearly says that this is black body radiation. Means is any material which is at a temperature will give out some radiation, electromagnetic radiation. So that is called as black body radiation. Fine, fantastic. We know this. We are very happy. The problem is like when we go to infrared, two things are happening. These sizes are increasing. The spot size is increasing. Even then it's a black body. But if you come to higher energy, we have a problem. The lower temperature should be darker. Expected, right? But it is the other way. It is very, very bright. Then it cannot be black body radiation. It should be something else. Okay, so that clearly says that our understanding of sun may not be complete. So something else is happening there. This is not only for sun, many other things also the same thing happens. This is a famous picture of crab pulsar. It is a rotating neutron star rotating at 33 times per second. Okay, so now this, when you see in the different wavelengths, unless and until you actually combine all of them, you will not get an idea that there is some very compact object rotating at the center, giving out energy in the two poles. So if you see any one of them, you wouldn't have got the full picture. So that is the reason why we need multi-wavelengths. Again, this is the answer. So this I'll just mention. When Hanley was built with 20 crores, Hubble took 2,000 crores, and JWST has actually taken 70,000 crores. Costliest mission and the biggest mission is 70,000 crores. But I have a full talk on this one only on JWST. Even that won't do justice because the kind of technology went into JWST. Each one requires one book. So this is the costliest and the largest man-made object ever flown. And this is our astrologer. We are going to peer very, very back into our past, almost up to Big Bang. Somebody saying that, okay, I am spending too much in the introduction itself. I'll stop it in two things. This is fine. Everything is fine because the light won't, some wavelengths won't reach Earth. So we need to actually go to space to observe them. Then why visible? Why Hubble? First of all, Hubble is working in visible and infrared. Sorry, UV. Okay. The reason is atmospheric seeing. What is atmospheric seeing? All of us are actually learned twinkle, twinkle, little star. Yes or no? What is twinkle, twinkle, little star? Twinkling of the star is nothing but atmospheric seeing. So because of the atmosphere turbulence, the photons which are coming, they will not come directly, they will start dancing around. So this dancing around will create some blurry effect. Okay. So this blurry effect, this is one of the images we call it as planetary nebula taken from Earth, the same taken from Hubble. You can see the reason between these two is because of atmosphere. Atmosphere is not only absorbing, it is actually blurring also. So two things are happening. To avoid this, even going to space in optical is useful. Okay, for large part of the spectrum, now astronomy has moved to space, and our AstroSat is one of the major instruments in for studying multi-wavelength of cosmos. So how do we go there? We use rockets, and our PSLV can lift up to 40 ton now. Okay, so the total mass of a PSLV is around 300 ton. So that is simple. So we are going to work against gravity using thrust, and we'll reach there. So these are the different stages of a rocket. So these two are called as heat shields because when it starts moving very, very fast, lot of heat is generated. To save the satellite inside, it will be covered with heat shield. Once if we go out of the atmosphere, this heat shield is thrown out, this is exposed, and these are the different stages: boosters, rocket, solid state, liquid fuel, all sort of things. Finally, we reach space. So these are the orbits I already mentioned. I talked about low Earth orbit, geosynchronous orbit. There are few more orbits where the satellite will always be seeing sun. We call it as sun synchronous. There is a orbit which goes around the poles. We call it as polar orbit. Like that, there are multiple orbits. Okay. So after that, let's come to India's space science program, I'm talking about only space science. I'm not talking about other aspects of India. So we have lunar, planetary, and solar and astronomy through 3 different levels. So this is, we have started in 1963 with Aryabhatta, sorry, first sounding rockets and then Aryabhatta. So now we have reached Chandrayaan 3, Aditya and Exposat and in between. So currently Chandrayaan 2 is actually taking observations. AstroSat is doing observations. It was launched in 2015. It has completed 10 years in September last year and now it is going strong. And then Chandrayaan 3 is on the moon. Then Aditya L1 and Exposat are also doing. Okay. In future, we have a UV mission which is going to provide the deepest UV images till now any other space agency. And another one is called broadband X-ray polarimetry. I will be talking about later. So this is Mars orbiter mission. It was launched in November 2013. You know that with Mars orbiter mission, India became the first country to reach Mars on its first attempt. Some people even made a comment that Mars orbiter mission is cheaper than autos in Bangalore. The amount of money spent per kilometer is cheaper than whatever the money autowalas demand. I don't know about Bhubaneswar. What is the rate in Bhubaneswar per kilometer? It's not there. Huh? Good. So in Bangalore, it has now reached to 30 plus rupees per kilometer. So it is, people used to say that it's much cheaper than that. We didn't use the Puri analogy, so don't go with the mission Mangalyaan. So, but we know that how to actually reduce the cost, and the total cost is 450 crores, including launch, including the satellite, including all the 7 payloads. When we say payloads, these are experiments. Okay, please remember that whenever I say payload, it is what we call it as an experiment on there, including everything. It had 450 crores. So it had carried one Mars color camera, Mars methane sensor, thermal imaging spectrometer, Langmuir probe, and Menka. We are very good at giving names: Menka, Ramba, Urvashi. We have a lot of names like that. Please don't ask me what is the expansion of that. I myself keep forgetting that. And you know the funny thing, most of them comes from only 2 places, either SAC or PRL. So key results are, it is the first time it took a full Martian disk in a single shot, and then it actually studied demos with that. Okay, so it actually took the full image and completed 8 years. It was supposed to work for 9 months. It took 9 months to reach, and it was supposed to work for 9 months, but it worked for 8 years. So we did lot of studies, including study of the Deimos for the first time. Deimos is one of the satellites of Mars, Phobos and Deimos. So Mars color camera has produced more than 1,000 images. We could actually see everything. So that clearly shows that there are civilization there actually pluffing, doing everything. Not true. Okay, AstroSat was launched in September 28th, 2015. It carried mainly 5 science payloads, one auxiliary payload. Professor Avahia was there at TFR when this was launched. And then we have ultraviolet imaging telescopes, soft X-ray telescope, and large area X-ray proportional counter. These 3, soft X-ray telescope, large area X-ray proportional counter, and cadmium zinc telluride imagers were made at TAFR. Ultraviolet imaging telescope was made at Indian Institute of Astrophysics, Bangalore. And then scanning sky monitor was made at URSC, URO Satellite Center in Bangalore under ISRO, in collaboration with ISRO. ISRO got it done. This is one of the best example for collaboration. You don't have to do everything on your own. Give it to the different institutes, different research institutes, and get them help you out. Okay, that's how ISRO works. Not only India, we also had 2 international collaborations who gave us sensors. For example, University of Leicester, they gave the image for the S60, camera for image S60, and Canadian Space Agency gave image for UV80. It's a camera, which is a CMOS camera, whatever you see in the mobile now. Advanced version of that was given by Canadian Space Agency. So AstroSat has observed from the nearest star. What is that? Sir mentioned that yesterday. Huh? Proxima Centauri, which is around 4.3 light years, and it actually found that similar to spots on Sun, Proxima Centauri also has that to the farthest 9.3 billion light years away. Okay, 9.3 billion light years away. So that means that that torch was switched on 9.3 billion years back. 9.3 followed by 9 zeros. So many years back, the torch was switched on, and we are seeing it now. And this is a discovery because till now, almost everybody to observe, and even they thought that this particular redshift range or the distance range should not give out any UV at all, because either UV will be absorbed from there or there will not be any UV. But AstroSat proved that no, it is not there. Now it is, we are working on that. The reason for that is, come to that one later, is this. So before that, Galax was the UV telescope from NASA. Our UV-AT is 5 times better resolution than that and higher collecting area. With this, we could get all these images, and this is the image from JWST. I mentioned that the costliest mission till now, 70,000 crores. JWST image, it's not that JWST is much better than AstroSat. We can very well complement. This is the JWST image, and these two lines, what is not there, orange, red and blue, is from AstroSat. So we can clearly see that some of the things which even JWST cannot actually resolve, we can provide information about that. So we match JWST in UV. So what are these payloads? You know that X-rays are very energetic. They cannot be reflected by a lens. They cannot be bent by a lens. Okay, so what we do is we use what is called as glancing angle. So whenever you go to a trip or somewhere, when any water body, what is the first thing you do? You start throwing your stone. Yes or no? You never threw stones into the water body? Some people, what, instead of throwing directly, they'll try to throw it at an angle so it skips. Okay, skips. That is the technology used to bend X-rays. I didn't know that there is an international tournament for skipping, and the highest number of skips is something around 2 dozen. The number of times it has jumped over. Okay, so when the X-rays are falling here, it will not just go through that, it will skip like this, so it will slightly bend. Using another saying, you bend it little more and bring them to a focus. So this is how SXT works. But if you go to little higher energy, even they will not be bent by glancing angle also. Then what we use as coded mask. How many of you watch this IPL? IPL, fantastic. How many of you have watched IPL matches overnight? Most of the matches are overnight, na? Okay. Whenever a person is walking, how many shadows do you see? How many shadows? How many shadows I am seeing here now? 1, 2, 3, 4. You just stand and see how many shadows you see. Why so many shadows? Light, different lights, right? So each shadow will tell you that there is a light source in that direction, right? So extend the same one. Only the problem is, if both of them are symmetric, you cannot say whether this light is coming from this direction, this direction. But if you make a mask here like this, some of them are open, some of them are closed, it will make a unique shadow. And this shadow will vary with the angle, right? So like the way you are saying that, but just by looking at a shadow, you say that at what angle, at what distance there is a source, you can reconstruct the entire sky by looking at the shadows. That is what is coded mask do. We use this for higher energies, higher X-ray energies, because they can't even be bent at a very shallow angle. Okay, and then there is something which simply passes through gas and ionizes it, and we calculate the energy of that. That is called as large area X-ray proportional counter. You can see the size of these things by looking at the people around that, the people who made it. So when it was launched, large area X-ray proportional counter had the highest collecting area in the entire world. Okay. So coming to Chandrayaan, we are very well aware of that, and yesterday I talked about this, so I am going to skip this. Just for continuity, I am saying that ISRO's or India's lunar program started with Chandrayaan-1, which detected water. Chandrayaan-2 confirmed it, and with Chandrayaan-3, we could actually land on moon. So we proved many technologies. So Aditya L1 is India's first solar mission. As I mentioned earlier, it is between Sun and Earth, Lagrangian point 1, which gives it a continuous observation time of Aditya. So with this, we are trying to understand the coronal mass ejection and heating, these science. So we can actually discuss it later. It carried 7 payloads. Okay, this is the orbit. Can you see this orbit? So it is not at point, it is going around that. I'm sorry, instead of L1, I have put L2, but this is the same, principle is the same. So it has totally 7 payloads, VELC, variable emission line coronagraph. Corona is nothing but, you know that during solar eclipse, total solar eclipse, when it completely becomes dark, you see slightly light outside that disk. This is, we call it as corona, which is at a much higher temperature. Can you believe the sun is around 5600 degrees centigrade, but the corona is million degree. So much temperature more. We want to study that. How we study it? By actually covering the photosphere. We try to study this corona. Okay. So this is what is called as the corona visible emission line coronagraph. Then we have in UV, which will be completely seeing the complete image of sun. That is called as solar UV imaging telescope. This is from again VELC is from IAA, Indian Institute of Astrophysics, Bangalore. This is from Ayuka, Pune. Solar low energy X-rays. It is from PRL, and Helios is from here. This one. This name is given by me. High energy L1 orbital spectrometer. So we are very good at giving names. Papa, now see the names. Papa, this is the particle spectro studies. These are the ones which study when the particles reach there. Aspects is also another particle. Magnetometer. This gives the measurements at this point where Aditya L1 is moving. So this is the first time the shutter of the suit instrument opened in 20. So you can please keep seeing this in the space. It's a real image, real video. And AstroSat had similar thing, but AstroSat was one-time operation. It will just open and permanently it will be there. But this can be keep on doing this. Okay, whenever we want, we can open it and close it. So these are some of the results from that. You can see that the quiet image, how the sunspot and everything using suit image in different wavelengths, how this looks like. Okay, and the energetic profile also we have taken. And I'll show you one coronal mass ejection. Keep looking at this portion. Can you see that ejection? It will repeat. Okay, I'll go back and I'll just play it again. Did you see? Maybe I missed it. Next time I have another one where actually it is coming out like this. I'll show that. This is a first image, so I am just keeping that. So is this data proprietary to only few people? No. This data is open to you also. All you have to do is use your email ID, register yourself in the player, whatever the web pages I have given, you can download the data. Not only download, giving the data away, we'll actually teach you how to actually analyze the data, interpret the data, and if you want to publish, we'll help all these things for all our missions. So for planetary, for this one MOM, for ISSTC, Astro Browsers, for UV, AstroSat, we have it freely available for everybody. And if you think that whatever the data already observed is not good enough, you can ask time on AstroSat. You can write a proposal saying that, see, I have a great theory. I want to do this observation to find out whether it works or not, you please give me time on AstroSat. We do that also. So AstroSat works as a proposal-based observatory. Even you are allowed to write proposals. So what are the upcoming missions? Now we have completed Chandrayaan, Mars orbiter mission, we reached there. So to continue with that, now currently we are working on Venus orbiter mission, which is expected to go or to move Venus in 28 to 30 range. And then followed by LoopX. I already mentioned about LoopX and Chandrayaan 5. So we are going to bring back samples from Chandrayaan, moon. And then we have, I don't know how I missed it. We have ISRO has plans to land on Mars using Mars lander mission. That is going again like Chandrayaan 5. We are going to send two rockets. One is going to, and with that one we are going to land on Mars. Shukrayaan is not the final version. Please take it as Venus orbiter mission. And then we are going to observe planets outside solar system. Selected some 500 plus stars, planets we are going to study and to look for biosignature. Want to see whether life may have existed or is there a possibility of life on other planets. So we are going to study them using our methane, water signature and other things using exoworlds. Daksha, whatever that X-ray sources I talked about, they are not constant. They will be variable. Means their intensity keeps on suddenly changing and coming back, and we will not know in which direction it is. So to study them, we have a Daksha which is going to be monitoring entire sky, all the 360-degree sky. Finally, we are going to look for signatures from the Big Bang Theory. Immediately after the Big Bang Theory, there was a long time when there were no stars. After stars formed, galaxies formed, and this first light, what we call it as epoch of reionization or the cosmic dawn, we are going to study using Pratyush. So I'm just going to talk about one future mission, that is ExoVerse. The way we are going to look for biosignature, study the atmosphere of planets outside our solar system is, we are going to select certain planets which are going around star. So when the star is in front of the, when the planet is in front of the star, whatever the information total you are seeing is the combination of star plus planet, right? So now when this planet is behind the star, whatever the information you are going to get is only from the star. If you subtract the two, in theory, you should get the information only about planet. Yes or no? We are going to do that. Okay? It's saying is very, very simple. It involves lot of complicated calculations, but this is in principle what we are going to do. With that, we are going to look for, so this is when only star is there, when planet is there, and then when the secondary, just when it is going behind. Okay, we are going to study all these things. So with all these things and with so many things available for us, I want to know how many of you will be interested in serving ISRO. Thank you. Fantastic. So you have a lot of opportunities. We have opportunity not only for scientists in all the fields. We need technicians who have completed their ITI, Industrial Training Institute test, and technical assistants with a polytechnic degree, and scientist engineers who have science background or engineering background. Almost all fields. You just tell me one field in physics or engineering, I'll say where it will be useful for ISRO. Any field. Okay. So we have openings for almost every field in science and technology, chemistry, biology, mathematics, physics. We are not against any of them. Anything science, we are ready. So IIT Trivandrum after 12th, we have a institute set up for training the people. So after PUC, you can actually join the training institute. If you actually fulfill after the training, if you fulfill, we will directly absorb you into ISRO. If not, we actually give you BTech degrees. So, and there is a lot of demand for that also outside. So we have an institute set up for that, which actually give degrees in BTech and avionics, aerospace, and physical sciences. In addition to that, we also provide MTech and PhD there. So not only this, there are a lot of openings for administration, because a institute or a research institute like ISRO needs a lot of administration also. So we have a lot of openings coming up almost every year for that. So this is your chance now. So before I close, I just want to mention about some very peculiar experiments done in space. Some of them are Voyager 1 and 2. Yesterday I showed you a picture of that PV. Do you remember? Earth's photo from Jupiter. That Voyager launched in 1977 is still going and going and going. So it has crossed so long from Earth. It has moved away so much from Earth. What may be the distance it might have covered till now? In light speed, it hasn't even covered 1 day. It was launched 50 years back and it hasn't even covered 1 light day. So the nearest star is 4 light years. How much time it might take? Just to tell you, there is a mission called Parker Solar Probe, which is going to touch sun. When I say touch sun, it's not going to launch there. It's going into the close to sun. At its highest speed, it will be moving at 200 kilometers per second. Even with that speed, we need something like 10 to 15,000 years to reach the nearest star. That's the fastest we have done till now. Okay. Then there are asteroids and moon. There are a lot of missions to asteroids. One of them is Psyche, and which is very, very metal rich, so much metal rich. And there is another asteroid which is pure diamond. If we can actually bring that asteroid onto the Earth, each one of us will get a few tons of diamond. So there is a Lucy, which is a study, which is going to go near that L3 and study Trojan asteroids. And we are planning to send missions to, not when we say we, it's not ISRO. We are talking about whole of space system. There are few missions which are going to study Europa, satellite of Jupiter, and fly. What is happening? Okay, so we are aware of a space station, right? International Space Station. Lots and lots of experiments are going on International Space Station. Even you can write proposals. Some of the major or interesting results are Kelly experiment. Two brothers, Kelly and Kelly, were selected for this. One was sent to ISS, and another one stayed on the Earth. Whatever he was doing there, whether he is walking, whether he is eating, whether he is doing exercise, the same thing this fellow did on Earth. So two were mirroring each other. After a few years of observation, when he got back, both of them were compared to find the effect of microgravity, now having less gravity in ISS. So this actually gave lot of information about the health and medical effects of microgravity. Okay, this is a Kelly experiment. And then we are trying to grow food in the microgravity environment. And when whoever, you might have seen, whoever goes to ISS and others, when they come back, they will be literally carried on two people. They will be walking like this. The reason is, our body is such that if you're not using any particular organ or anything, it will lose its functioning. So since they are in the gravity, so the bones and others need not work so much to carry our weight. So it will keep on losing its density, bone density will reduce and everything. They will be so brittle, it will become so brittle. If you actually kick somebody, it might actually break. So these are the things we have to study if we want to actually go and stay in some place later. So you heard of Artemis anyway. So as I mentioned, whatever the speed with which we are going to reach the nearest star will take tens of thousands of years. To avoid that, there is a concept called solar sail. Instead of actually trying to use the fuel to go there, we are going to use that sail. You know that sailing ship with a lot big sail. So whenever there is a matter from sun, it will hit the sail and it will push it. With that, we are trying to reach very high velocities of lakhs of kilometer. So it will reduce the time required to reach the nearest place. We call it a solar sail. So that way, the sail is going to be some 1 kilometer size. Solar sail, 1 kilometer size. I don't exactly remember, but that is one of the concepts. Okay. Finally, Lisa. So gravitational waves, I talked about gravitational waves. Something similar we are attempting to do from the space with 3 satellites kept away at 25 million kilometers. And we should know that value to millimeter accuracy. You are talking about 25 million kilometers and then accuracy is millimeters. That's the kind of experiment we are trying. I think. So with that, I'll come to the end and I'll put up my thank you. Yesterday it was given, yesterday it was come directly, na? Why we are doing this now? Okay, it's just a thank you note, but I wanted to use that quote by Carl Sagan. The cosmos is within us. We are all children of stars. So each one of us are carrying some stardust in us. Okay, we are all stars, born stars. I'm not joking. I just want to ask you why I am saying that. How do we know that? How do we know? So when the universe was formed in the Big Bang, most of the universe is made out of mainly 2 elements. What are they? Hydrogen and helium. Okay, only 2 elements. And the stars act like pressure cookers. They cook higher elements. To then once the hydrogen combines to form, all the hydrogen is exhausted. So we will be cooking helium and helium to carbon, nitrogen, etc. Okay, all these things will be start to glow. But at one point, this stops. Once these elements become iron, beyond that, instead of giving out energy, you have to give energy to that to produce higher elements. So iron is the most abundant because of this. Okay, iron is the stop. So if you want to make more than that, then you have to provide energy. But all of us have gold, silver, everything. How did that come into picture? On Earth also we have gold, silver, much higher than lead. This is where the supernova explosions and others comes into picture. The supernova explosion, so much energy is released that these iron and above elements are cooked in that one. And the same elements we are seeing that, so we are formed from the matter which was thrown out by a supernova explosion. Okay, so that clearly shows that all of us have some part of a star. Thank you very much. Questions? Can you just give me that? Can you give me that?
Good afternoon, sir. So
Good afternoon.
my question is, what are white dwarfs?
Okay. Just give me 1 more minute. Just a few seconds. Yesterday I was talking when I was talking about lunar program. So I told you that this is a place where our Chandrayaan 3 landed and we called it as Shiv Shakti. This is Shiv Shakti point. You can see there is a stone just away from that. We call it as Nandi. Nandi in front of Shiva temple. Bullock. Okay. Who is the question? Somebody has the question.
So what are white dwarfs?
See, our sun, assume that there is a star like our sun. So he's actually burning hydrogen at the core and converting that into helium, and he is getting the energy out of that. So once all this hydrogen is converted into helium at the core, what happens? That it will stop. Now you have two opposing forces. Initially, when hydrogen is burning into helium, it is releasing radiation, photons and everything. This will be pushing out, and its own weight will be pushing it down. So two things are acting opposite. Now you suddenly switch it off, and there is only gravity. So this gravity will actually condense it. It will start pushing it inside, and it will become smaller and smaller. Okay, till it reaches a point where, yesterday we heard about Bose-Einstein condensation. Like that, there is something called electrons. There will be too many electrons. They will be coming closer and closer and closer. Since this is at a very, very high temperature, the matter, whatever it is, it cannot be in the neutral stage. It will be ionized. There will be more and more electrons released. Okay, so these electrons, they don't like to be pushed to very, very close. When it reaches a stage where electrons are very, very close, immediately electrons say, hey, stay, I don't want you to closer than this. So this will show some opposition. This is the opposition pressure. This we call it as electron degenerate pressure. If the mass of the star initially, if it is around 1.4 solar mass, this is what is Chandrasekhar has given this limit, and hence the name Chandrasekhar limit. So if it is less than that, then this electron degenerate pressure is good enough to stop further collapse. Okay, so star, our sun, which is around 6 lakh kilometers in size, will be pushed to our Earth size, something around 6,000 kilometers. At that time, this electron degenerate pressure stops the further collapse. And during that, some of the outermost layer will be thrown out, leaving out mainly core. So the core will be at very, very high temperature of the order of 25 to 30,000 degrees centigrade. So hence it is called as white, because at 25,000 degrees, you will be getting pure white light. And because it has become smaller and smaller, almost 100 times smaller than that, hence dwarf. So this is white dwarf.
Sir, I have another question. So what are supernovas and how are they formed?
Sir is saying that he is going to tell all these things tomorrow.
Okay, thank you, sir.
Yes, he's.
Morning. Good afternoon, sir.
Good afternoon.
Sir, as you told about
Nose.
neutrinos, they are massless, and millions of them are passing through our body right now even. So if they are massless, then how we are able to identify them, their existence?
Good question. Initially, it was identified only through theory, because these are these are spin half particles called as leptons. Okay, so if you actually write a equation for fusion, hydrogen plus hydrogen is equal to helium plus gamma ray. There are two half spin particles, hydrogen and hydrogen. Helium is again half particle spin, so you need another half. Where did it go? That's where they brought in one particle. But this has already satisfied the mass. They could not give mass to that. That's how it came into existence. So they are doing experiments. So even though millions are of them passing, that means that its interaction is very, very weak. But if we have large enough detector, you might detect one or two of them. Maybe it takes years, but it will detect one or two of them. So there are many, many experiments which are going. Kamiya Kande is one. Prasavahya. Japan's Kamiya Kande is the first detected neutrino. There are other places where in poles, for example, South Pole, they have made millions, kilometers wide detectors. So to detect one or two interactions.
Sir, my another question is, sir, we know that universe is expanding, and we are not able to even explore the whole entire universe. So how we got to know that universe is expanding?
Sir, he is saying that he will answer tomorrow.
Sir, you told that there are different type of stars in the universe. Some are very, very big, and some are smaller than even a town or Earth. So stars are generally made up of the gases, hydrogen, helium. So why can't be the Jupiter, which is large enough than the Earth, can be a star?
Good question. So he will give the answer tomorrow again. No, they don't know. They don't know. Okay. In one answer, I'll say that the necessary. See, you know this matchstick, right? How many of you use a matchstick? So do you really say that each time you strike it, you will get a fire? Many times you have to do it multiple times, right? What's the reason? The temperature or the heat generated by the strike may not be enough to actually ignite it. So similarly, the conditions may not be enough to actually start nuclear fusion. It needs pressure, it needs certain temperature. He's going to talk tomorrow. So it is not enough in Jupiter. Yes. Yes, ma'am. She.
Good afternoon, sir. So, when you were talking about Aditya L1, for anything to orbit around an object, it needs to have a gravitational field or to actually rotate around it. So, how does Aditya stay in the orbit if there's no orbit around? Like you said that it moves around the L1 point.
Very good question. Will you
But-
answer this tomorrow? He will answer.
Actively you told about neutrino. So my question is, why do neutrino have such tiny masses compared to other particles? And what does this hint at physics beyond the standard model?
It is following standard model. It came as a theory, but we know because it has to solve certain things. Yesterday, when we are talking about chemical equations, so you have to equilibrate, like you have to actually, what should I say? Balance. So I am talking about a physical equation which has to be balanced, and hence we arbitrarily put neutrinos. Then for later on, we started looking for it and we found that. So this is to balance out certain things like spin, momentum, all sort of things. It follows all the rules.
So my another question is, could neutrinos help explain the antimatter imbalance in the universe?
As of now, no. Tomorrow, okay. So like Einstein, his astronomy, he'll talk. Okay.
Okay, sir.
Good afternoon, sir. So my question is that, sir, you told earlier that E is equal to mc square is an ultimate formula found on Earth. Is there any limitation or any case where this formula got contradicted?
So next
See, the
question.
thing is, I am giving you patchwork of information because I am not able to give you a continuous explanation. It will take me another
Sir
90
will be
minutes.
talking about all these astronomy
Ah.
related stuff tomorrow. He is asking you, or requesting you
He
not
is
to.
a specialist in space sciences, space technologies, about satellites, movements of satellites, planetary missions, etc., etc. You want to know that from him.
ISRO.
And ISRO, yes. And the worldwide programs, actually.
Yes.
So my another question is that we got many results and peaks from missions like Chandrayaan and Gaganyaan. Sir, but you earlier mentioned the Europa, that satellite of Jupiter. So have we got any information till now?
We haven't launched. They're all in the planned missions. They are going to go there.
Thank you, sir.
And also, it's not ISRO mission. Yeah. No, okay, he's actually doing.
Good afternoon, sir.
So my question, so my question is, did we find the L points? Like
L1 points,
yeah,
Lagrange
L1,
points.
L2 points.
I was talking to somebody. It's a very good question, and I want you people to actually try to think a bit about it, because I'm not going to give the answer now. It's easy to understand about L1 because you have sun here, you have earth here. Both of them have attractive forces. At some point, the attraction due to this will be cancelled out by this. At some point, it will be zero. It is very easy to explain.
It's a null point, basically.
You can say that it is a point where effectively you will not fall either here or not there, but it is an unstable point. If you come little closer to here, you will go towards sun. If you come little closer to earth, you will fall towards earth. It is an unstable point, but there is a point. But to explain the other 4 points, you need not only gravity, you need rotations and orbital motions also, centrifugal and centripetal forces. I am going to leave that as an exercise to you.
Then and all the other points like L4, L5, they also follow the same.
Exactly. So, but it is not only gravity which is actually defining those points. In addition to that, you have to use Coriolis forces and other forces.
Okay, thank you, sir.
Good afternoon, sir. Sir, as you were speaking about the upcoming missions and all, sir, you spoke about Lupix and Chandrayaan. Sir, are they both same or
No.
like what is the aim
No.
of Lupix?
One of them is Chandrayaan 4, another one is Chandrayaan 5. Maybe that is a easier way to tell you. Chandrayaan 4 is going to land very close to South Pole, closer than whatever Chandrayaan 3 did, and it is going to study the permanently shadowed regions and look for ice and other elements, and it will not send the sample back. With Chandrayaan 5, we are planning to bring back the sample from there. The reason is this: when you are sending something onto moon, you will have lot of sample, but you cannot have lot of experiments to do there because mass is limited. But if you bring back sample, you will have less sample, but you can subject that into multiple experiments. Some of them might need a 1 ton size mission to do the studies, which we cannot send it there, right? So that the Chandrayaan 5 is going to bring back the sample. You can call it a sample return mission.
Thank you, sir.
Good evening, sir. Good afternoon, sir. Sir, kindly let me know the role of computer science engineers at ISRO.
We need computer science from data analysis to define the orbit to actually finding out where exactly and what time we have to launch to avoid certain things. All these things are requires computers. Finally, writing project reports also requires computers.
Thank you, sir.
Communication requires computers. Let me actually not go into very detailed studies. In fact, I just found out from our this ISRO that ISRO is working on at least some 24 AI tools which will be useful for us. All of them requires computers.
Good afternoon, sir. My question is that this origami is used to make compact for satellite.
ISRO has not attempted any of them as of now. It is in the concept stage only. But ISRO is working on something other than that, reusable rockets and maybe some of the material which can reduce the debris problem. So we are working on that, not origami.
Sir, I had it's not exactly a doubt, but what is the actual use of the gold layering on the satellites?
Okay,
and all?
very good. It's not a gold layer, it is called mylar. So what happens is whenever light is falling on that, you will see that so when you go out in the sun, you will see that you actually skin will start getting burnt. So how to avoid that? Some people use gloves or some people use a full length this one. So what how you are doing that? And also second thing, whenever you do that, what color you use? Black?
Generally white.
White. Why? Because it will be reflected more, right? Black will absorb more, it will be reflected more. This is one easy way of actually stopping it by reflecting more light. So golden, that mylar layer, whatever we use, reflects most of the light back to save inside from temperature. And at some level, it actually stops the other radiation also.
So what's the material? It's
Mylar.
mylar. Okay. Is
My-
it a combination or?
It's a combination of some 2-3 things, Kapton and mylar. I don't know the exact ratio.
So I always thought it's a gold layer.
No,
so
it's
that's-
not gold.
Thank you, sir.
It's not gold. Color is gold color. In Kannada, we call it as Kage Bangara. Kage Bangara is mica. You know that, right? So it's a Kage is crow in Kannada. So Bangara is gold. So it's just very similar to that, but it's not gold. How much time? How many more questions I can take? Couple more.
Good afternoon, sir.
Hmm.
So my question was that you taught us about dark matter, and
I mentioned about dark matter, but I'm leaving it to him. I'm not
Oh.
answering that.
Good afternoon, sir. So my question was like Chandrayaan 3 worked for like the rover worked for 14 days. After that,
Not 48 days, 14.
14. Huh,
14,
I mentioned
okay.
14. 14 Earth days. But as you mentioned that Chandrayaan 4's rover will work for
100 days.
approximately 100 days. How are you going to achieve that?
Okay. The reason for the non-recovery of Chandrayaan 3, we were just hoping in hope that it might come up after 4 days. The reason is, during the night time, means lunar night, the temperature goes to minus 200 plus. Okay, it will fall below minus 200 plus. Whatever the instruments, whatever the components, everything, whatever we have measured or certified is up to minus 150 or minus 170. We didn't go beyond minus 200 because it takes a lot of effort and make it sure that it works below that. So none of these things will work below that. Okay, so two things are needed now. Either you make the components to withstand this temperature. I don't know how many people have seen this or not. During the cold weather, the battery life of your mobile and everything falls a lot. Now imagine at minus 200, your batteries will stop working. Then the next time when you want to start the batteries again to charge and everything, it will not be possible once it completely depletes, completely dies off. So you might have seen that your car battery or the bike battery, if it goes off completely, you have to take it to the mechanic and he will have a special equipment to charge it. Normal charging will not stand. So similarly, once this battery is gone, you can't do anything. So for 100 days, what we are planning to do is, we are not going to reach that minus 200 degrees. So whatever the critical components, whatever the critical items in this one, they will be kept at certain temperature. What is the temperature? I'm not sure now, but we are going to keep it at a temperature. How do we keep that? By actually providing some energy to that. So that might be generated by radioisotopes. Nuclear, whatever you read, radioisotopes. With that, we are trying to keep that at a certain temperature so that they will not die off till the sun comes. That's how we are trying to achieve 100 days.
Good afternoon, sir.
Good afternoon.
Sir, we know that America launched the Apollo 11 mission. So now that time technology was not well developed. Now we are having high quality cameras and good technology. So why is America not doing any significant contribution in exploring moon or something?
They are doing it. It's not that they're not doing now. With Artemis, they're again going back. This is the first case which they tried. Okay, they're doing it. If the question is why there's a gap of 50 years, that I can answer. But if you say that Americans are not attempting, no, they're not attempting with Artemis. Okay, so I'll tell you about this. How many people have watched Durandar movie? Okay, my next question is, how many times? One, two,
one time.
Okay, if I make you watch it for 7 days, 7 continuous times, 7 times, how many of you will like the movie Durandar as you are liking it now? How many will like it? Why? It's the same movie, same actors, same theater, everything same. Why you stopped hating Durandar now? Hate is a very strong word. Why you are not liking it anymore? The reason is, The novelty is lost. First time Americans went onto moon, that is the first. Oh, he came first, and we tried it. And second time they went and they said that okay, we went there second time and we did this experiment, this experiment. Third time, the charm is lost. If somebody says Americans went to moon, oh, they have already done. Why they are going again and again? Yeah. The reason is this: whenever you involve life, it costs almost 100 times more effort and cost than if you send a mission. If the mission will work better than humans to do the same experiments, then why you spend more money, more this one, just to send something which this person does at a lower level? So that's why they stopped it. It's not that they lost all the technology. There was the returns was less. The novelty is lost. People, that's why people say that all of you remember Neil Armstrong, you don't remember
sir.
Buzz Aldrin. Same way, you extend the same analogy.
Sir, one more question. We know that Sun is a luminous planet and
Sure.
luminous star. So, what makes it luminous?
ಕನ್ನಡದಲ್ಲಿ ಒಂದು ಗಾದೆ ಇದೆ, ರಾತ್ರಿ ಎಲ್ಲ ರಾಮಾಯಣ ಕೇಳಿ ಬೆಳಗ್ಗೆ ರಾಮನಿಗೂ ಸೀತೆಗೂ ಎಂದು. You heard so many things about nuclear fusion. I talked about nuclear fusion, how the neutrinos comes and everything. Nuclear fusion is the one which is actually giving energizing the star.
And sir, we say that it will be like decaying or destroying after many years. Sun.
Yes.
So why it happens? Like
Because
nuclear reactions.
Assume that you are actually having a car. You want to go from here to Visakhapatnam. You have filled your car. You have started with a car. Unfortunately, your car comes with a closed petrol tank. After some time, you cannot fill the petrol tank, or you lost the keys to the petrol tank. What happens? How far you can go? Can you keep on going further? At some point, when the fuel is over, you have to stop. Na? That is what is happening there. It started its life with a given amount of hydrogen. It is not infinitely replenished. After some time, all the hydrogen will get converted into helium. It is not even all the hydrogen. In the core, the hydrogen gets completed into helium. At that point, that fusion stops. That we call it as beginning of death.
Yes, sir.
Okay, so again the same question. I think two more questions. Last two more questions. Sir is actually asking me to get down from the stage.
Sir, my question is that a lot of satellites are surrounding the Earth. What happens once they complete their purpose?
After many years, they will come down, reach Earth's atmosphere and burn down. But it will take a very long time, and it's going to be a problem. What we call it as debris.
So, will it cause problem while launching new sun?
It is causing it is causing problems already, and we are going to add tens of thousands of satellites to that. Already what is happening is each of our launch, earlier we used to fix the time to the seconds. Now we have to keep it open till the last minute. We do calculations, see that there are no debris, and we modify the launch time such that there are no debris on the way. We are already into that level, and these launches are happening few minutes apart. But maybe in future, we may not even get a time when rockets can be launched. It's going to be a serious issue.
Sir, I have another question. You mentioned that the moon orbiter mission was supposed to be only for 9 months, but it was
Mars orbiter.
Mars orbiter mission. My mistake. It was supposed to be only for 9 months, but it worked for around 8 years. How was that possible if the fuel was only for 9 months?
Exactly. So whatever the fuel, which is most of the times what happens is the fuel, whatever it carries, is to actually correct the orbit around that. If whatever calculate, we usually carry little more, and if we never uses that for correction, that kind of correction, then that fuel will be forever be available. Most of these components and everything will go through so many rigorous testing that they can survive much longer than their design life. Most of the times it will be minimum double. So here fuel is the only question. If you are not at all using the fuel, it will be permanently there. Last question.
Sir, what do you think about the vision of ISRO? Would ISRO will dominate the space market with a low budget fund in upcoming years?
Why do we try to dominate something? Is there a particular reason to dominate? Right? We can coexist. My next talk is going to be that. How you can coexist in nature. You don't have to always fight.
Thank you, sir.
Any other questions? Oh, thank you.
Thank you very much, Professor Girish, for such an
Thank you all.
enriching session.
Thank you all. Even though I have to get down from this one, if you still have during lunchtime or in the evening, ma'am is going to show the sky. So I will be tomorrow 2 o'clock onwards. There is going to be 2 hours of continuous grueling. So we will be sitting here. You can use whatever gun you have to fire at us. Thank you very much.
Thank you very much once again. Please give a big round of applause, please.